This section looks at major components of the 4-stroke and 2-stroke petrol engine. Because they operate on similar principles, many of their components are similar too. For example, their engine blocks both operate under working conditions of very high pressures and temperatures. And new designs and materials to make them work more efficiently are always being tested. Many vehicles still use cast iron, but some have aluminium alloy blocks. The main gain is a saving in weight. Aluminium alloys can be made as strong as cast iron, but they're lighter. This is also true for cylinder heads. Combustion chambers in the cylinder head come in many different designs. To help hold in the extreme heat and pressure of combustion, a seal is made between the block and cylinder head by a head gasket. The 4-stroke petrol engine has other passages cast into the head to carry oil for lubrication and coolant for cooling. In a 2-stroke petrol engine, lubrication occurs by mixing oil with the petrol, so oil passages are not needed. And if, like many 2-strokes, air cooling is used instead of liquid cooling, there's no need for coolant passages in the cylinder head. Another difference between 4-stroke and 2-stroke petrol engines is how they deliver air-fuel mixture to the cylinder. In a 2-stroke petrol engine, separate passages called ports let air-fuel mixture into the crankcase and cylinder and exhaust gases out. They're covered and uncovered by the piston as it moves up and down the cylinder. In the 4-stroke petrol engine, the inlet and exhaust ports are opened and closed by valves. These valves need a system to control how they work. The valve is held in place by a valve guide with a spring on its stem. A rocker arm is attached to a stationary shaft that allows the arm to pivot. The rocker arm compresses and releases the valve spring so that the valve opens and closes. The valves need a system to control how they work. This is done by using cams. A cam is a lobe on a shaft. It's specially shaped to open the valve, hold it open and let it close. The cams control the valve action, but what drives the cams? Cams are attached to a camshaft. In modern vehicles, it's usually mounted over the cylinder head and is called an overhead camshaft. Intake and exhaust lobes can be on the same shaft, or there can be a shaft each for intake and exhaust. Notice that in this design there's no need for rocker arms. It's a much simpler arrangement. A camshaft can also be mounted in the engine block near the crankshaft. As the camshaft rotates, motion is transferred through the pushrod to the rocker arm. It pivots and opens the valve. The camshaft keeps all of the valves working in sequence, but all of this still must always happen at the right time. Air-fuel mixture must enter at the right time in the cycle, and the piston must be in the right place when the exhaust valve opens. The position of the piston is crucial, but what determines that? The crankshaft. It helps to synchronize all this activity. In one cycle of a 4-stroke engine, from intake through compression, ignition, power and exhaust, how many times does the crankshaft turn? Twice. It makes 2 revolutions. During that time, what happens to the valves? They open and close once. So the cams must turn through just 1 revolution, as does the camshaft. In each cycle, the crankshaft turns twice and the camshaft only once. So the camshaft must turn at half the speed of the crankshaft. One way to do this is with gears. One of these gears has 40 teeth and the other, the driving gear, has 20. When they mesh, the larger one rotates at half the speed of the smaller. If these gears are separated but linked with a chain, it makes them turn in the same direction, but they still turn at their same speeds. If the smaller gear is on the crankshaft and the other is on the camshaft, how fast does the camshaft turn compared with the crankshaft? Half the speed, just what the system needs. The position of the ports is important for how mixture enters the cylinder and for how burned gases leave it. Removing exhaust gases is called scavenging. If they aren't fully removed, it reduces engine efficiency. Some engines use a deflector on the piston crown. It directs air-fuel mixture up towards the spark plug and exhaust gases down towards the exhaust port. This reduces the amount of incoming mixture escaping through the exhaust port and helps remove exhaust gases. How scavenging occurs depends on the design of the cylinder and ports. Crossflow scavenging occurs when mixture enters on one side of the cylinder and exhaust gases escape on the other side. No valves are used and mixture flows across the cylinder. Loop scavenging means mixture enters the cylinder across the top of the piston and is caused to flow upwards in a loop before moving in the direction of the exhaust port. In a two-stroke petrol engine, the oil and petrol are usually mixed before they enter the engine. Different engines use different ratios, as given in manufacturers' specifications. Oil, air and petrol enter the crankcase. The high temperatures vaporize the petrol and the oil lubricates the moving parts. A four-stroke petrol engine crankshaft is basically the same as that in a two-stroke. At first, the shape may be a surprise. Why won't a simpler shape do the job? It's all to do with balancing forces. With its weight evenly balanced, this top spins properly. By adding a magnet, it now becomes unbalanced. Without removing this magnet, how can the top be made to spin properly again? Put an identical magnet on the other side. Then the weight is balanced again. The second magnet acts as a counterweight. Counterweights appear in unusual places. They're essential for some systems to work at all. Crankshaft counterweights help keep the rotating components in balance. They help keep the crankshaft turning as smoothly as possible. The crankshaft turns because of the forces transmitted through the connecting rods. At the same time, it must be held in place. That's done by bearings. They reduce friction and allow free movement. The crankshaft is held in place in the engine block by main bearings at points called journals. Different bearings do different jobs. These bearings support the crankshaft in place but let it turn freely. The crankshaft also needs to be located to stop lateral movement. This is done by using flanges. Between the connecting rod and the crankshaft are connecting rod bearings. They protect the spinning crankshaft at points also called journals. On the rear of the crankshaft is a heavy flywheel. It stores up energy from the power stroke and helps keep the crankshaft turning. In a four-stroke engine, only one of the four strokes in a cycle delivers power. In one cycle, the crankshaft makes 2 revolutions. In a two-stroke, every second stroke is a power stroke. Without the flywheel to store energy from the power stroke, the crankshaft will slow down and stop.